When engineers sit down to design a pipeline, a turbine, or an aircraft, they often start with a mathematical dream, the ideal fluid. To make the math work elegantly, classical physics relies on two core assumptions. First, this hypothetical fluid is perfectly incompressible. You cannot squeeze it into a smaller volume. Second, it is perfectly inviscid, meaning it flows without any internal friction. We translate these assumptions into a mathematical blueprint, the ideal stress tensor. Notice the main diagonal. Those are the normal pressure variables pushing against the fluid. But look at the off-diagonal slots. They are all zero. The ideal fluid experiences zero internal shear stress. The problem with this perfectly uniform, frictionless liquid is that it does not exist anywhere in the universe. Every real fluid resists flow. Every real fluid compresses. Relying entirely on ideal equations in extreme environments, like deep-sea architecture or human blood flow, guarantees mechanical failure. To build systems that actually survive the physical world, we have to discard the mathematical illusion. We have to look at the microscopic origins of density and viscosity. We are taught early on that gases can be compressed, but liquids cannot. Put a liquid under extreme pressure, and that rule breaks. Even water, the standard benchmark for an incompressible substance, shrinks in volume when pushed hard enough. To measure this, physicists use the volume modulus, quantifying the pressure required to force a change in a fluid's volume. The relationship is rarely static. As you squeeze the liquid, the modulus scales upward linearly. The harder you press, the more aggressively it pushes back. This resistance to compression dictates how a fluid transmits energy, specifically sound waves. A sound wave is simply a traveling disturbance in density. Looking at the equation for the speed of sound, we see it relies entirely on that stiffness. The rate at which pressure changes with density governs the exact speed of the wave. We measure this packing of matter in three ways. Density is raw mass per volume. Specific gravity compares it to water. Specific weight factors in local gravity. Why do some fluids compress easily while others act like concrete? It lies in their microgeometry, mapped by the radial distribution function. Under pressure, a highly structured molecular array locks in place, resisting compression. A randomized, chaotic layout contains empty space, allowing molecules to condense. What we observe as macroscopic incompressibility is actually a highly rigid molecular geometry hidden out of sight. Now we return to our broken stress tensor from earlier to fix the second assumption. We have to replace those zeros with the mathematical manifestation of internal friction. This is viscosity, the fluid's inherent resistance to shear deformation. It is the drag you feel when stirring a thick liquid. There is an assumption that heating any fluid makes it run thinner. That is false. Temperature affects gases and liquids in entirely opposing ways. In a gas, viscosity is driven by momentum exchange. Imagine two layers moving at different speeds. Molecules from the fast layer dart into the slow layer, transferring momentum. This equation defines gas viscosity, highlighting the average molecular velocity. Heating a gas gives its molecules more kinetic energy. They move faster, cross layers more often, and collisions become more violent. In a gas, heat increases viscosity. Liquids operate differently. Packed tightly, momentum exchange is negligible. Liquid viscosity is driven by electromagnetic attractive forces, pulling like stretched rubber bands. Heating provides kinetic energy to snap these bonds, allowing layers to slide. Heat decreases liquid viscosity. Viscosity is never a static number. It is an ongoing war between kinetic energy trying to rip molecules apart and structural forces binding them together. Down at the microscopic scale, a fluid is a violent, chaotic environment. A suspended pollen grain will continually jerk and vibrate in random directions. This is Brownian motion, the erratic dispersion of particles through a fluid, driven by invisible thermal collisions. This equation links that random microscopic diffusion directly to macroscopic viscosity. Macrodiffusion and macroviscosity are inversely locked together, pivoting entirely on the thermal energy of the system.
The exact same water molecules randomly slamming into the pollen grain to push it forward are the very same molecules creating the viscous drag that resists its movement. It is a single mechanism viewed from two different angles. This unification of thermodynamic behavior was formalized in 1905 during Albert Einstein's miracle year. Through this lens, a fluid's macroscopic resistance to flow is merely the aggregated statistical shadow of billions of microscopic collisions. Everything we've discussed so far assumes the fluid is Newtonian, meaning its viscosity stays constant no matter how hard you shear it. Water and air act this way. Many industrial fluids do not. This graph maps shear stress against shear rate. A Newtonian fluid is a perfectly straight line. Non-Newtonian fluids, however, change geometry under stress. Now notice this new curve starting higher up on the y-axis. It belongs to Bingham plastics. That starting point on the y-axis is the yield stress threshold. Below this specific threshold of force, the material refuses to flow at all. It acts as a rigid solid. Inside a pipeline, this creates a unique dynamic called plug flow. The center core of the material doesn't experience enough shear stress to breach the threshold, so it moves as one solid, unbroken block. Only the material grinding against the pipe walls liquefies. Other materials exhibit viscoelasticity. Modeled here as a Maxwell fluid, they possess both liquid viscosity and solid elasticity. When compressed, they flow, but they maintain a fading mechanical memory of their previous shape and slowly rebound. Because the fluid's internal geometry actively reorganizes to fight the flow, classical equations fail to predict their behavior. You have to account for the material's changing structure. Understanding these properties allows us to scale up to massive geological systems. Consider an underground aquifer, where water must weave through miles of solid rock. This is Darcy's law for flow through porous media. Look at the equation for hydraulic conductivity. It isolates the variables beautifully. On one side, you have the immovable stage, the rock's geometric permeability. On the other side, you have the actors, the density and viscosity of the fluid itself. Scale up further to planetary engines. Deep in the mantle, minute shifts in density create massive thermal cycles. We see Rayleigh-Benard convection, driven entirely by gravity acting on cooler, denser material. In zero-gravity environments, this halts, weaving Marangoni convection, which cycles fluid using only gradients in surface tension. To calculate these massive geological churns, physicists use the Boussinesq approximation, a mathematical hack where they assume fluid density is completely constant except for the exact moment they need to calculate buoyancy. If we collapse our perspective from planetary geology down to biology, the physics shift again. A human falls into a pond and sinks. An insect lands on the exact same water and walks across it. This is quantified by the bond number, a ratio comparing the downward pull of gravity against the upward push of surface tension. Gravity scales with volume, but surface tension scales with length. As an organism gets smaller, its volume drops significantly faster than its length. Insects operate in a physical realm where gravity is practically irrelevant and surface tension is a solid floor. Fluid density actively filters evolutionary survival. When an underwater predator rapidly expands its jaws, it creates a low-pressure vacuum. Because water and the prey share roughly the same density, the rushing water carries the prey right into the mouth. Air is 1,000 times less dense than water. Attempting that exact same suction technique on land is physically impossible. The air simply slips past the prey. This single variable of fluid density forced terrestrial animals to evolve completely new jaw mechanics to survive. When we design a high-pressure pipeline, calculate planetary magma flows, or map the evolutionary anatomy of a predator, we are looking at the exact same variables. Density and viscosity are the invisible architects of the physical world.